600 light-years away, a star the size of our entire solar system just collapsed inward on itself. And for the first time in recorded human history, we may be about to watch a star die with our own eyes. Not through a telescope, not through data, naked eye, in broad daylight, bright enough to cast shadows at night, bright enough to confuse every migratory bird on this planet, every whale navigating by starlight, every ancient astronomical instrument ever built. And here is what no one is saying out loud. We don't know exactly when. It could be tonight. It could be in 10,000 years. But the collapse has already begun. We are watching it in slow motion, and we are almost certainly too late to predict the final moment. But here's what keeps astrophysicists awake at night. It's not the explosion itself. It's what Betelgeuse did in 2019 and 2020 that changed everything we thought we understood about how stars die. An event so anomalous, so unprecedented, that scientists invented a new category just to describe it. What Betelgeuse did has never been observed in any star in human history. And what it means for us, for Earth, is something the headlines are not telling you. To understand what Betelgeuse is, you first have to confront a scale that your brain is not built to process. Our sun, the star that makes life on this planet possible, that drives every weather system, every ocean current, every photosynthetic reaction, in every leaf that has ever existed, our sun is roughly 1.4 million kilometers in diameter. That number is already beyond intuition. You could fit 1 million Earths inside it. Betelgeuse is 700 times larger than that. If you place Betelgeuse at the center of our solar system, where the sun sits right now, its surface would extend past the orbit of Jupiter. Not Earth, not Mars, Jupiter. The gas giant that dwarfs every other planet in our neighborhood would be swallowed whole, orbiting times inside, times the star's outer atmosphere. That is not a metaphor, that is geometry. And this is the star that is dying. Not slowly, in the way we used to assume stars die in the gradual billion-year dimming that happens too incrementally for any civilization to notice. Betelgeuse is dying times now. In astronomical time, now means within the next 100,000 years. But what happened between October 2019 and February 2020 suggested something far more immediate, something that forced astronomers to revise their models, their timelines, and in some cases, their fundamental assumptions about stellar evolution. The star dimmed dramatically, catastrophically, by a magnitude that had never been recorded in modern observation. And for several months, no one could explain why. That unexplained dimming has a name now, and the name tells you everything about how shaken the scientific community was when they finally understood what caused it. The year is 1987, February 23rd. A Chilean astronomer named Ian Shelton is working through the night at the Las Campanas Observatory in the Atacama Desert. He is developing a photographic plate. This is still the era of physical film, and when the image resolves, he sees something that should not be there. A point of light in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, that was not there the night before. He walks outside into the cold Atacama air and looks up with his naked eyes. And there it is, visible without any instrument at all. A star dying 168,000 light-years away. Its death light finally arriving at the precise moment Ian Shelton happened to be pointing a camera at the right patch of sky. Supernova 1987A. The first naked-eye supernova in nearly 4 centuries, since Johannes Kepler observed one in 1604. But here is what most people don't know about SN 1987A. The star that exploded Sanjulik, negative 69 degrees, 202, was not supposed to be able to explode. Not according to the models that existed before 1987. It was a blue supergiant, and the prevailing theory said blue supergiants didn't go supernova. They were too hot, too compact, structurally wrong for that kind of catastrophic collapse. Reality disagreed. The shockwave of neutrinos, nearly 10 billion for every square centimeter of Earth's surface, passed through every human body on this planet 17 hours before the light even arrived. The explosion announced itself in particles that moved through solid matter as if it didn't exist, and we detected it. Underground detectors in Japan and Ohio registered the burst simultaneously, giving us 3 hours of advance warning before anyone could see anything with their eyes. 3 hours. That is how much warning the universe gave us. And that was for a star 168,000 light-years away. Betelgeuse is 600 light-years. The neutrino burst from its times explosion would arrive months before the light. We would feel it in our instrument, in our data before we saw it. And then the sky would crack open. Between October 2019 and February 2020, Betelgeuse lost roughly 2/3 of its visible brightness. For a star that has been one of the 10 brightest objects in the night sky for as long as humans have recorded the sky, this was not a subtle fluctuation. Ancient observers, Mesopotamian, Greek, Arab, Chinese, had all catalogued this star. Medieval astronomers knew its name, Ibn al-Jawzar, the armpit of the giant, from the Arabic. For millennia, Betelgeuse had been reliably, predictably luminous. Then it wasn't. The initial hypothesis was simple: a pulsation. Betelgeuse is a variable star, meaning its brightness naturally oscillates in cycles. Astronomers expected this. What they did not expect was the scale. The dimming was so severe that it dropped Betelgeuse out of the top 20 brightest stars in the sky for the first time in recorded observation. Social media declared a supernova imminent. Late-night television made jokes, and inside observatories around the world, nobody was laughing. Two competing explanations emerged, and for over a year, data supported both of them, which meant neither could be ruled out. The first, internal cooling. A massive convective cell, a bubble of plasma the size of Earth's entire orbit, had risen to the surface, cooled, and temporarily darkened a significant portion of the star's visible face. Dramatic, but survivable. A stellar weather event. The second explanation was something else entirely. Scientists called it a surface mass ejection. Not a solar flare, we know those. Not a coronal mass ejection like our sun routinely produces. Something categorically larger. Betelgeuse had shed a piece of itself. A mass of hot plasma equivalent to several times the mass of our moon launched outward, cooling as it traveled, condensing into a cloud of silicate dust that partially eclipsed the star from our perspective. The star had physically injured itself, torn away its own outer atmosphere. Think about what that means. A star so massive, so energetically unstable in its final evolutionary phase, that it is literally losing pieces of itself into space. Not in the slow, steady stellar wind every star produces. In violent, catastrophic eruptions that leave scars. The Hubble Space Telescope captured the aftermath. A vast, asymmetric cloud of cooling dust, still expanding, still moving away from the star it was ripped from. A wound in space, visible from 600 light-years. But what the follow-up data revealed in 2022 changed the interpretation completely, and it suggested something that even the most measured, cautious astronomers found difficult to dismiss. Both explanations were correct, simultaneously. The surface mass ejection had triggered the internal cooling event, or the cooling event had enabled the ejection. The causal direction is still debated. What is not debated is the conclusion. Betelgeuse had experienced something that no other star had been observed doing: a coupled, cascading failure of two distinct atmospheric systems at the same time. This is not stellar weather. This is stellar times deterioration. There is a particular kind of vertigo that astronomers describe, not all of them, but enough that it appears in memoirs, in interviews, in the quiet conversations that happen after conference. The vertigo of temporal displacement. When you look at Betelgeuse tonight, the light entering your eyes left that star approximately 600 years ago. That is not a figure of speech. You are not seeing Betelgeuse as it is. You are seeing it as it was in roughly 1425 CE, when Joan of Arc was still alive, when the printing press had not yet been invented, when no European had seen the Americas. The star you are looking at may already be gone. It may have exploded centuries ago, and the light from that explosion, a shockwave of photons traveling at 300,000 kilometers per second, is currently crossing the void between us, getting closer every second. And we will not know it is coming until it arrives. Dr. Andrea Dupree, the Harvard astrophysicist who led much of the post-Great Dimming research, described the experience of studying Betelgeuse not as scientific detachment, but as something closer to medical diagnosis. "We were watching something happen to a living system," she said in a 2022 interview, "and the system was telling us something was wrong. The question was whether we were smart enough to understand the message." The message, as it turned out, was written in a language that required entirely new instruments to read. The velocity field of Betelgeuse's surface, the way different regions of the star are moving toward or away from us, showed asymmetries that the models had not predicted. One hemisphere of the star was behaving differently from the other. A star the size of Jupiter's orbit was not moving as a unified system. It was moving in times pieces. For the researchers who had spent decades studying Betelgeuse, this was not an academic observation. Edward Guinan, an astronomer at Villanova University who has tracked Betelgeuse's variability since 1983, longer than most of his graduate students have been alive, described the period of maximum dimming simply: "We were scared, not in a personal way, in a professional way. We felt like we were about to miss something, or worse, that we had already missed." That particular fear of arriving too late, of the universe having moved on, before the instruments caught up, is one of the defining psychological conditions of modern astronomy. The universe operates on timescales that dwarf human civilization, and yet the critical moments, the transitions, the collapses, happen in fractions of seconds. A star lives for 10 million years and dies in 45 minutes. And here is the human dimension that the data alone cannot capture. If Betelgeuse goes supernova in our lifetime, not in 10,000 years, but in our lifetime, every human being on this planet will experience it simultaneously. There will be no specialist knowledge required, no telescope, no app. You will walk outside and there will be a second sun in the sky that was not there yesterday. It will be visible for weeks. It will be visible in the daytime. It will cast shadows at night sharp enough to read by. The last time something like that happened, SN 1006, a supernova so bright it was recorded by observers in China, Egypt, Iraq, Japan, Switzerland, and the indigenous peoples of North America. There was no global communication, no shared experience. Every civilization saw it in isolation and tried to interpret it through the frameworks it had. This time, 8 billion people would see it together, in real time, simultaneously. What that moment would mean psychologically, culturally, philosophically, is something no scientist can model. But every astronomer who has thought seriously about it describes the same quiet certainty. Nothing would be the same afterward. Not our relationship to the night sky. Not our intuition about permanence. Not the casual, unconsidered assumption that the stars we were born under will be the same stars we die under. When Betelgeuse finally collapses, when the iron core at its center, built through millions of years of nuclear fusion, finally reaches a mass that gravity cannot be denied, when the outward pressure of fusion stops for the last time, and the star falls inward at a quarter of the speed of light, the collapse itself will take less than a second, less than 1 second. A star larger than the orbit of Jupiter. Gone, in the time it takes to blink. What follows is one of the most violent events the universe is capable of producing. The infalling material hits the newly formed neutron core, a remnant the size of a city, but with the mass of our sun compressed into a sphere 12 kilometers across and rebound. The shockwave that propagates outward carries more energy than our sun will emit in its entire 10 billion year lifetime. In those first seconds, Betelgeuse will briefly outshine the combined light of every other star in the Milky Way galaxy. 600 light years away, that light will arrive at Earth compressed into a pulse of radiation, optical ultraviolet X-ray, that will be intense enough to affect the upper atmosphere. Not catastrophically, not at this distance. The science is clear. 600 light years is far enough that Earth is not in danger. The ozone layer will absorb the high-energy radiation. The biosphere will survive intact. But here is the revelation that the Great Dimming delivered the thing that nobody expected from what appeared to be a stellar weather event. Betelgeuse is not behaving like a star that has millions of years left. It is not behaving like a star with hundreds of thousands of years left. The surface mass ejection of 2019 to 2020, the asymmetric oscillations, the recovery patterns when fed into the most current stellar evolution models suggest a star that is deep in its final evolutionary phase. Not imminent in human terms, but imminent in stellar terms. And stellar terms, in this case, may be closer to human terms than anyone is comfortable saying publicly. The light we will see when Betelgeuse explodes left that star 600 years ago, which means the explosion itself, if it has already happened, is already racing toward us, already crossing the void, already 600 years into a 600-year journey that ends the moment it reaches our eyes. There is no way to know if tonight is that night. There is no early warning system for a star this close. There is no alarm. There is only the sky and the habit of looking up, and the possibility, the genuine, scientifically unresolved possibility that you could walk outside tomorrow morning and find that the universe has changed while you were sleeping. And then there is the question that every conversation about Betelgeuse eventually reaches, the one that scientists phrase carefully and laypeople ask direct. What are we exactly watching? Not just a star dying, we are watching the forward. Betelgeuse, in its final fusion cycle, is manufacturing elements in its core that only supernovae can produce: gold, uranium, iodine, the selenium in your body right now, the iridium in the boundary layer that marks the extinction of the dinosaurs. Every heavy element in the periodic table above iron was made in a dying star, made in a moment exactly like the one Betelgeuse is approaching. When Betelgeuse explodes, it will seed its corner of the galaxy with the raw material for future planets, future oceans, future life. The death we are waiting to witness is not an ending. It is, in the most literal sense possible, creation. The astronomer Carl Sagan said we are made of star stuff. He was not being poetic, he was being precise. The calcium in your bones was forged in a stellar core that collapsed billions of years before this planet formed. The iron in your blood came from a supernova. You are, in the most direct and physical sense, the product of a star that died. Betelgeuse is about to do the same thing, for someone else, somewhere else, a billion years from now. We spend most of our lives assuming the sky is static, that the stars we name and navigate by and tell stories about are permanent fixtures, furniture in the universe's room, reliable and unchanging. Betelgeuse has always been there, in the shoulder of Orion, one of the most recognizable constellations in human history. Every culture on Earth has a name for that pattern of stars. Every child who has ever looked up at a winter sky has seen it, and it is ending. Not as a failure, not as a loss, in any final sense, but as a transformation so extreme that the word ending barely applies. Betelgeuse is not disappearing, it is becoming something else, a neutron star, possibly a black hole, a nebula of expanding gas and dust that will be visible from Earth for thousands of years, a new object in the sky where a familiar one used to be. The universe does not do endings, it does transformation. And we are alive, improbably, briefly, in exactly the right moment of history to potentially witness one of the most dramatic transformations in the observable universe happening to a star close enough to see with our naked eyes. That is not a small thing. That is not a scientific curiosity for specialists in dark rooms with telescopes. That is the universe making itself visible to anyone willing to step outside and look up. Look up. But here's what this video hasn't told you. The neutron star that Betelgeuse leaves behind if the collapse follows current models will be one of the most extreme objects in the known universe. A sphere 12 kilometers across, spinning hundreds of times per second, with a magnetic field a trillion times stronger than Earth's, emitting beams of radiation so precise and so regular that when astronomers first detected them in 1967, they genuinely considered whether they were receiving a signal from an intelligent civilization. They called the signal LGM-1, Little Green Men. What they had actually found was a pulsar, the corpse of a dead star, broadcasting to the galaxy. What Betelgeuse becomes after it dies, what it broadcasts, and what we will be able to learn from it that is the next chapter of this story. And it begins the moment the light arrives.